All right, we are almost ready to talk about chemical bonds. Let's review first. Remember that the number of protons of an atom will tell you what element you have. The number of neutrons will tell you what isotope you have. And then the number and the distribution of electrons that you have will tell you the chemical behavior of that element. Is it willing to react with other elements? Is it not willing to react? Is it inert? And if it is willing to react, how does it? Does it take electrons? Does it share electrons? Does it give electrons? And so if you recall, atoms with an incomplete valence shell can share or transfer valence electrons with certain other atoms. And anytime you have this exchange of electrons or sharing of electrons, this results in those atoms sticking really close together and resulting in the formation of a chemical bond. There are different kinds of chemical bonds. We're going to talk about three major types: covalent bonds, ionic bonds, and hydrogen bonds. We'll start at the beginning of this list and tackle covalent bonds first. A covalent bond is the sharing of a pair of valence electrons by two atoms. The nice thing about this sharing is that in that covalent bond, the shared electrons count towards completing the valence shell of both of the atoms involved in the bond. Let's take a look at a really simple example. The example we're going to use here is a covalent bond forming between two atoms of hydrogen. So if we're looking at hydrogen, remember hydrogen is the first atom on the periodic table. It has one proton. To be neutral, it needs to have one electron. And so it's got one electron in that first shell, but that first shell can fit two electrons. And so hydrogen does not have a full valence shell, but it would like to have a full valence shell. So this is where we can take two atoms of hydrogen. Right? So one atom says, well, I've got one electron. And the other atom says, and I've got one electron too. We would both like to have two. So why don't we just come together and share the two electrons that we have between the two of us? And remember that both of those electrons in that bond now count towards completing the valence shell of both of the atoms involved. And what this does is it creates a molecule of hydrogen. So we went from having two hydrogens on their own, each having only one electron, to them coming together to share that pair of electrons they have between the two of them to form a molecule. So a couple of things we're going to have to introduce here. We have to introduce what is a molecule, and then you'll notice down at the bottom of the screen here, you have hydrogen molecule, H sub 2. If we go back to our carbon example, remember we were talking about how do you write things out around that element symbol, and we have those four corners in the box, imaginary box drawn around the atomic symbol. You've got your atomic number on the lower left-hand corner, your mass number in the upper left-hand corner. Well, we're missing two corners, this one and this one. If you have a number in the lower right-hand corner, this automatically tells you that what you're looking at is a molecule. You have covalent bonds here holding the atoms together. And it'll tell you how many of those atoms you have. So in a hydrogen molecule, you've got two hydrogens. Or if you're looking at H2O, if you're looking at water. If you don't have a number in the lower right-hand corner, that implies you just have one of those atoms. So one oxygen, and then you've got two hydrogens. Or CO2, carbon dioxide. In this case, you've got one carbon, and you've got two oxygen atoms, right? So lower right-hand corner indicates how many atoms of that particular element you have in your molecule. And now we're not going to spend a lot of time looking at the upper right-hand corner, but just a little bit of a preview. This is a space where you're going to add the charge. So if this is a charged molecule or ion, it's going to have a positive or negative charge. So for example, you can have sodium. Sodium is Na. If it's a sodium ion, it'll have a plus there. It has a single positive charge. If it's multiple charges, it'll be like calcium, it'll be 2+, right? If it's just a plus, it indicates one positive charge. Or chloride ion, that's got a negative charge, so it'll have a minus in the upper right-hand corner. So upper right-hand corner tells you charge and how many of those charges there are. Okay, so back to our definitions. What is a molecule? a molecule is when you have two or more atoms held together by covalent bonds. These atoms can be the same element, can be different elements, doesn't matter, so long as you're holding two or more atoms together using specifically covalent bonds. We're going to talk about other kinds of bonds. Other kinds of bonds don't form molecules, though. Only covalent bonds form molecules. Now, you can have single or double covalent bonds. When you have a single covalent bond, this is where you have sharing of only one pair of valence electrons. If you've got a double bond, this is where you're sharing two pairs of valence electrons, meaning 4 electrons total are being shared between the two atoms. And examples, if we go back, let's say water, right? So H2O, you've got a hydrogen, and you've got oxygen, and you've got a hydrogen. So hydrogens and oxygens in this case are the hydrogens and the oxygen are going to be sharing one pair of electrons between the two of them. And so a single covalent bond is shown as a single solid line. On the other hand, if you have a molecule of oxygen, those two oxygen atoms are sharing two pairs of valence electrons, and so you'll signify that double covalent bond as two solid lines between those atoms. Okay, and it makes a lot of sense if you think about the valence of these particular elements, right? So hydrogen has a valence of 1, it can form one bond, so 1 and 1. And if we take a look at oxygen, right, oxygen is our 8th element. So think about it for a second. 8 protons, 8 electrons. 2 electrons go in the first energy shell. That one's full. That leaves 6 for the second energy shell. Second energy shell fits 8. So really oxygen needs 2 more electrons. That has a valence of 2, right? And so here you've got 1 extra electron shared there and 1 extra electron shared there. Here, both of the oxygens need 2 more electrons. So they're just going to share 2 pairs of electrons. And so each one gets those extra 2 electrons, and they're both going to be happy, have that full valence shell. So they need that double bond to be satisfied. Okay, now there are different ways to represent molecules. The ones that I drew out just a minute ago, those are all pretty simple molecules, and so it's easy to draw out the structural formula for them. And a structural formula will show you all the different atoms and how they're connected. So you'll see all the covalent bonds, all the solid lines drawn between them. So for example, this is going to be a structural formula here for water. This is a structural formula here for oxygen, a molecule of oxygen. But sometimes molecules get really, really complicated, and there are a lot of atoms involved. And we as scientists, we get lazy sometimes, and we don't want to draw out the whole thing. And so we can abbreviate a molecule using the molecular formula, where we simply just state, here are all the atoms involved, here are all the elements involved, and here are the number of atoms of each. So a molecule of hydrogen, for example, will be H sub 2. If we go back to our examples here, water, the molecular formula, right, is H2O. Oxygen gas here is O2, right? So those would be the abbreviated or molecular formulas for those molecules. All right, and so here are some examples of the 2 different molecules. You've got oxygen, you've got water, and different ways of looking at them. So you've got your molecular formula, you've got your electron distribution diagram. Anytime you have the electron distribution diagrams and their electrons shared between overlapping energy shells, that's an indication that that's a covalent bond and those electrons are being shared. So in this case, you have 4 electrons being shared here in the middle, and that's pretty easy to tell that that's going to be a double covalent bond. Down here we've got water, and the oxygen and the hydrogens, they're only sharing 1 pair of electrons, so those are going to be single covalent bonds. You've got your structural formulas for each of the molecules, and then your Lewis dot structures as well. So if you would like to get a little bit of practice drawing the Lewis dot structures, they're pretty much like electron distribution diagrams, but you're just using dots just to show the valence electrons found in the atom. And so here you can see that there are 4 valence electrons that are being shared between the 2 oxygen atoms. Whoops, let's go back. And then lastly, you've got the space filling model. So what I encourage you to do maybe here is stop the video for a second and ask yourself a couple of questions. First of all, ask yourself, are these two examples that I'm giving you here, oxygen and water, are they molecules? See if you can determine that. See if you can determine whether they are compounds. Go back to the definition of what a compound is. Is each one of these a compound? Is either one an element? Go back to the definition of an element. Is this an element? And see if you can figure out yes or no for each of those. So is it a molecule, a compound, or an element? And then why did you pick those options? Okay, one more thing to add to complicate covalent bonds a little bit, right? So covalent bond is when electrons are shared between atoms. Now, atoms are kind of like kindergartners. Sometimes they share really nicely, and other times they don't share very nicely at all. And one atom will kind of hoard the electrons towards itself and not give the other atom its fair share of the electrons. And so this attraction that atoms have to electrons within a covalent bond is called the electronegativity. This particular image you see on this slide, this is not something that's in your textbooks, but I've added it here to show you the relative electronegativities of elements on the periodic table of elements. And you don't have to memorize this, just understand the trend. So the trend is, if you go from the lower left-hand corner, where you see a lot of blue, up sort of on a diagonal to the upper right hand corner where you see the red, electronegativity is going to increase. So fluorine is red. Fluorine is the most electronegative atom on the periodic table. And then its closest neighbors like oxygen and nitrogen are also fairly electronegative. And then as you get further away from that fluorine, things kind of loosen up a little bit and the atoms don't pull as hard when they're sharing electrons in covalent bonds. And carbon, hydrogen have kind of equal electronegativities. They're both green here on this particular chart. And so if you have atoms, some pull really hard on shared electrons and others don't pull very hard, you can have different kinds of covalent bonds being formed depending on which atoms you're pairing together. And so if you have a non-polar covalent bond, this means that the atoms are sharing the electrons equally. And there are no charged poles that occur when you have a non-polar covalent bond, right? So equal sharing. So an example, if we go back here, oxygen, right? Oxygen is next door neighbor to fluorine. It's very electronegative. But when you have two oxygen atoms in a molecule of oxygen pulling equally as hard, like Hulk versus Hulk in tug of war, right? It's going to be a draw. They're going to share those electrons very much equally. On the other hand, when you pair oxygen, as is the case here in water, with two hydrogens, oxygen is very electronegative and hoards electrons towards itself. Hydrogens are really weak and they're like, sure, here, go ahead, oxygen, you take electrons from me. You're going to have an unequal sharing of those electrons between the oxygen and the hydrogens. And this results in polar covalent bonds. So here we have an example of a water molecule. And when you have these polar covalent bonds, what can happen is you can have the creation of what is called a polar molecule. So the oxygen, being very electronegative, hoards electrons towards itself and develops a partial negative charge. The symbol, lowercase delta, and the negative sign indicates a partial negative charge. It's not a full, but it's a partial because the electrons spend more time around that oxygen than they do the hydrogen. So the hydrogen atoms losing control of the electrons develop partial positive charge. So this water molecule here becomes polar. One end has a partial negative charge and the other end has a partial positive charge, simply resulting from that unequal sharing when you have those polar covalent bonds.